fatigue after
Yes.
COVID. So that is there. That is still there, but I am 95% covered.
Okay. Thank you. Thank you for accepting the invitation.
Thank
So
you, my pleasure.
I would request Professor Gigi Roy, the Chairman PhD, to conduct the Viva, please.
Okay. Good afternoon to everybody, and especially Professor Bhattacharya, who is the external examiner today. Glad to see Professor Bhattacharya, you are fine. And
Thank you.
okay. Because nowadays each and everybody is getting
each and
somehow.
everybody.
Yeah. We do not know when our turn will come. So this is the situation is like this. Anyway, very good to see you. And then Anushree will defend his PhD seminar today. Anushree, you can start and do not take more than 40 minutes. Okay, and then Professor Bhattacharya will take up. Okay, you can start.
Okay,
Just
I am putting my video off so that
everybody. Yes.
Thank you, professors. Good afternoon, respected professors and dear colleagues. I am Anushree Dutta. Today I will present my PhD defense seminar on effect of cooling rate and aluminum content on microstructure, mechanical properties and oxidation behavior of nickel 0.9 to zirconium 0.08, 100 minus X, aluminum X is varying from 0 to 4 atom percent, nano ultrafine eutectic composites under the supervision of Dr. Jayanta Das. My work is introduction, literature review, experimental results and discussion. This consists of 4 chapters. First one is effect of cooling rate and composition on the microstructure and mechanical properties of nickel 0.9 to zirconium 0.08, aluminum 100 minus X, aluminum X, nano ultrafine eutectic composites. Second one is stranded sensitivity and deformation mechanism of nano lamellar gamma nickel Ni-base eutectic at room temperature. Third one is strengthening nano ultrafine lamellar nickel 88.32, zirconium 7.68, aluminum 4 eutectic by precipitation hardening, and final chapter is superior oxidation resistance of nano ultrafine nickel zirconium aluminum eutectic composites in the temperature range 500 to 900 degrees centigrade. And finally, I will present conclusion and followed by scope for future work. We know eutectic and near-eutectic alloy exhibit low melting temperature with superior castability. In eutectic reaction, liquid is transformed into two solid phase. And here we can find that in a eutectic phase diagram, the lowest melting point is the eutectic point where entire microstructure is eutectic with two phase. And in pro-eutectic composition, some portion of pro-eutectic phase is involved along with the eutectic microstructure, which changes the mechanical properties and other properties of the alloy. And several parameters which influence the mechanical and properties and other properties of alloys, such as interlamellar spacing, secondary dendritic arm spacing, which are controlled by composition, ternary alloy element, cooling rate. And the motivation of my work, nano ultrafine eutectic composites have been developed in titanium iron, tin titanium iron, gallium iron, niobium alloy system, which composed of hard intermetallic phase and soft solution phase. This alloy exhibited excellent superior mechanical properties, and ternary alloy element observed to alter the mechanical microstructure and improve the mechanical properties. Now, nickel-based alloys possesses high thermal stability, superior mechanical properties, and heat resistance properties. Therefore, nickel-based alloys is very suitable for developing nano ultrafine eutectic composites. Definition of my problem. So far, the microstructure and mechanical properties of the nano-eutectic composites have been developed in mainly titanium iron-based system. However, the room temperature microstructure and mechanical properties has been investigated in nickel, zirconium, aluminum alloys up to 4 atom percent aluminum content. These alloys exhibited superior room temperature properties, and therefore nickel, zirconium, aluminum composites has been chosen as a model system in order to investigate the room temperature as well as oxidation properties in detail. Therefore, the effect of cooling rate, aluminum content on microstructure and mechanical properties, stranded sensitivity, deformation mechanism, precipitation, hardening, and oxidation behavior of this nickel 0.92, zirconium 0.08, 100 minus X, aluminum X, up to 4 atom percent NECs are of interest, which were not investigated so far. My major objective of my work is to study the effect of cooling rate and evolution of microstructure and resulting mechanical properties of these alloys, and to correlate the effect of fast rod diameter on the evolution of various microstructural parameters to measure the bulk hardness, strength under compression, and correlate with the adopted cooling rate. My second objective is to explore the standard sensitivity and activation volume at room temperature of these alloys with lamellar thickness varying from 39 to 275 nanometers to reveal the deformation mechanism giving up to 15% deformation plastic strength, giving 15% plastic strength to compare the standard sensitivity and activation volume of this nickel zirconium aluminum NEC with the other reported FCC and BCC polycrystalline alloys and eutectic alloys. And third objective is to study the effect of annealing at 800 degrees centigrade on the evolution of microstructure and resulting mechanical properties of nickel zirconium aluminum NEC to assess the microstructural evolution and precipitation hardened composite through transmission electron microscopy, and to study the thermal stability, microstructure stability at high temperature up to 1000 degrees centigrade. And the last one is to explore the effect of cyclic oxidation behavior up to 120-hour oxidation at 500 to 900 degrees centigrade of this nickel zirconium aluminum NCs and their individual constituent phases in form of microcrystalline single phase of pure nickel, gamma nickel, and Ni5 jetted to analyze the oxidation mechanism and rate exponent, rate constant, and to explore the effect of nano, ultrafine, lamellar microstructure and aluminum content in the alloy on the oxidation properties. Parketal first synthesized nickel 92 zirconium 8 eutectic alloy in 2 mm diameter rods consisting of 20 to 30 micrometer size primary dendrites embedded in a eutectic matrix of 100 to 200 nanometer lamellar spacing. This microstructure of these alloys is comprised of FCC's gamma nickel solid solution dendritic phase embedded on an eutectic matrix of gamma nickel and Ni5 zeta phase. These alloys exhibited excellent mechanical room temperature strength and plasticity up to 1.6 GPa and ultimate composite strength 2.6 GPa with plastic strength 22%. The nanolamellar eutectic matrix imparts high strength, whereas the interaction with the gamma nickel dendrites and shear bands prevents the catastrophic failure. In 2015, MIP thus reported the alloying with aluminum modified the microstructure of the binary nickel zirconium eutectic in terms of their volume percent of the constituent phases, dendritic arm spacing, eutectic lamellar spacing. The volume percent of the dendritic phases observed to be increased from 20 to 29%, whereas the eutectic refinement of the eutectic matrix observed from 75 nanometer to 150 nanometer. My experimental part of my work is I prepare the ingot and rods of diameter 2 mm, 3 meter, and 5 meter in arc melting technology and in situ suction casting technology. After that, I some of the samples I anneal and some of the samples I oxidize to check their annealing properties and oxidation behavior. And microstructural characterization includes metrography, oxidation, optical microscopy, X-ray diffraction, scanning electron microscopy, transmission electron microscopy, whereas thermal differential thermal analysis I have carried out. It has been carried out, and mechanical characterization includes compression test, standard jump test, bulk hardness. My alloy composition lies. This is my alloy composition. Now, results and discussion, as I told, that is comprised of 4 chapters: first, effect of cooling rate and composition of this and microstructure and mechanical properties of this nano ultrafine eutectic composite. Second one, standard sensitivity and deformation mechanism, and third one, strengthening of nano ultrafine lamellar eutectic by precipitation hardening, and final chapter is superior oxidation resistance of nano ultrafine nickel zirconium eutectic composites in the temperature range 500 to 900 degrees centigrade. The first one is effect of cooling rate on composition of and composition on the microstructure and mechanical properties of these alloys. The X-ray diffraction pattern of this at room temperature shows that the 2 distinct phases are present in the alloys, that is gamma nickel and Ni5 zeta. X-ray diffraction pattern of the gamma nickel phases is shifted towards the lower 2 theta value, which shows that the change of lattice parameter with addition of aluminum content, whereas the no peak change of peak position of Ni5 jether upon aluminum addition, whereas the in gamma nickel and Ni5 jether peak position of gamma nickel and Ni5 jether remain unaltered with change of casting thickness from ingot to 2 millimeter diameter rods. The lattice parameter, as estimated using grid-built refinement analysis, is given here. The lattice parameter, we can observe the increase of lattice parameter with aluminum content for gamma nickel phase, whereas no change of lattice parameter for Ni5 jether phase in for both for 2 millimeter, 3 millimeter, and 5 millimeter rods. The microstructure scanning electron microscopy analysis shows that the gamma nickel dendritic phase embedded on an eutectic matrix, bitter eutectic matrix, which is for x equals to 0, whereas the gamma nickel dendritic phases percentage, volume percentage increases with aluminum percentage. We can observe that the percentage of the darker dendritic phase increases with at x equals to 4 alloy. Whereas the refinement of the gamma nickel dendritic phase can be observed in 5 millimeter and 3 millimeter diameter rods. And in higher resolution microscope, higher resolution image, we can find that this brighter eutectic matrix is actually composed of two phases, that is gamma nickel and Ni5 jether phase. And the refinement of the microstructure has been observed in 3 millimeter diameter rod. The EDS analysis shows that the dendrites is mainly composed of gamma nickel, and whereas substantial amount of the aluminum is present in the dendrite phase, whereas matrix is mainly composed of nickel and zirconia. The aluminum dissolves mostly in gamma nickel dendritic phase. The quantitative analysis shows the volume percent of the gamma nickel phases for all the ingots and rods changes from 20 to 21%, 31%, whereas the secondary dendritic arm spacing is refined in smaller cast diameter rod, and interlamellar spacing also refined in smaller cast diameter rod. Interlamellar spacing for 3 millimeter diameter rod from center to periphery varies from 100 to 130 nanometer. The bulk hardness and compressive strength, as I measured, it is observed that bulk hardness and compressive strength increases in smaller cast diameter rod substantially, and whereas small decrease of bulk hardness and casting strength decreases in aluminum containing composites. The cooling rate and growth velocity. Cooling rate I measured estimated from Jackson-Hunt model, and from this equation, from this two equation, and it is the cooling rate for this 2 millimeter diameter rod is estimated to be order of 10 to the power 4 Kelvin per second, and the cooling rate for all the diameter rod is given here, and the yields, the variation of yield strength and hardness with cooling rate is plotted in this diagram. It shows that the yield strength and hardness is linearly increases with the cooling rate. The summary of this chapter: alteration of cooling rate in the range of 10 to 10 to the power 5, 10 to the power 4 Kelvin does not influence the evolved phases, lattice parameter, and supersaturation. However, aluminum addition increases the volume percent of the gamma nickel dendrite from 20 to 31% with departing solidified composites. SDS has been varied from 2.3 to 39 to 6 micrometer, and gamma and lamellar thickness varies from 39 to 275 nanometer. Very high strength is obtained for all the NECs, which is varies from 1.16 to 1.6 GPa. Now, my second chapter is strain rate sensitivity and deformation mechanism of nanolamellar gamma nickel Ni5 jether eutectic at room temperature. The strain rate sensitivity and activation volume is measured using strain rate jump test. Two jumps is given. First jump where strain rate is varies from 8 into 10 to the power minus 5 per second to 8 into 10 to the power minus 4 second, and in second jump 8 into 10 to the power minus 4 to 8 into 10 to the power minus 3. In all the cases, we can find that the flow stress is increased with increase of strain rate. That is positive. The alloy is exhibited positive strain rate sensitivity value. The strain rate sensitivity value has been calculated from this equation, and whereas activation value volume has been calculated from this equation. And the alloy exhibited very low N value, which is lies in the range of 0.00 8 to 0.0102, which indicates the deformation, dislocation, this deformation mechanism is activated for this nanolamellar epoxy composites. The standard sensitivity value and activation volume is plotted and compared with the other polycrystalline BCC and FCC alloys and other lamellar epoxy alloys, where we can find that the M value of our NECs is lies in between the FCC and BCC. In FCC polycrystalline alloy, we know that the standard sensitivity value increases with decreasing of lamellar thickness. So, and in BCC, it is different trend, opposite trend is observed. In our FCC nickel-based NEC also follows the similar trend of FCC polycrystalline superalloys. However, their value of the standard sensitivity somewhat smaller than the similar grain size design for the other polycrystalline FCC alloys, and the activation value volume also compared with the other alloys, and activation volume lies within the range of 29 to 29.7 to 49.8, which indicates the dislocation mediated deformation mechanism is the controlling mechanism. Now, transmission electron microscopic structure of the deform up to 15% as solidified ingots shows that the dislocation, several dislocations are introduced in the microstructure after deformation. We can find the dislocation substructure, dislocation pile and several fragmented lamellae after deformation, after heavy straining, and some of the lamellae overlap with each other, and dislocation pile observed, and the several faults and band structure is we can find, and fragmented lamellae, lamellae become fragmented, and the SAD pattern differently oriented crystals has been observed, which indicates the introduction of dislocations and the lamellar bending due to the heavy straining of the composites. And deformed 2 mm diameter S-class rods also shows that the dislocation is introduced after deformation, and dislocation substructure, we can find a dislocation substructure and lamellar bending, dislocation pile, fragmented lamella become fragmented, and the slip planes and several slip lines which makes at angle 66 degree, which indicates the formation of 110 dislocation and 1-to-1 dislocation after deformation, and the several band pattern is observed after deformation. The high resolution image of the gamma nickel and NiTride shows that the lattice rotation of the gamma nickel phases in several regions of the gamma nickel lamellae, whereas in effective pattern, it can be observed that the nickel zirconium lattice crystallinity has been destroyed in some portion of the NiTride lamellae, where effective pattern shows the amorphous-like structure, whereas the some of the region crystallinity is maintained with shows the crystalline pattern, effective pattern. Dislocation pile-up we can see the dislocation pile-up slip lines and several planar faults after deformation. And standard sensitivity value, here standard sensitivity value is plotted with the variation of lamellar thickness. We can find that the standard sensitivity value increases with decrease of lamellar thickness, and whereas the standard sensitivity value decreases with the addition of solid atom. Then both the value from the standard sensitivity and activation volume, it is confirming that the dislocation mediated deformation mechanism actually is controlling for this NECs, whereas the HRTM microstructure also confirms that the dislocation mediated deformation because mechanism for the entire lamellar thickness region from ultrafine 39 to 275 region, the dislocation mediated deformation is controlling mechanism. The summary of this chapter is standard sensitivity and activation value of this NECs lies in the range of 0.008 to 0.0102, whereas activation value is 29.7 to 49.8 BQ. The presence of interlock lamellar microstructure causes small change of M as compared to the other polycrystalline alloys. And the HATM investigation of the partially deformed NEC revealed that the dislocation and lamellar interaction and their pile-up at the interface dislocation cutting with porous dislocation lamella enter, followed by the propagation of deformation band and cutting the lamellae into the island control the deformation process for both NECs. The M and V values of the NECs measured from the stranded junctures also confirm the disorganization mediated plastic flow in the entire range of lamellar thickness. The increase of solute content reduces the stainless sensitivity value for a given lambda W, which has been also predicted from the developed model. My third chapter is strengthening of nano ultrafine lamellar nickel 88.32, zirconium 7.68, aluminum 4 eutectic by precipitation hardening. In this slide, the X-ray diffraction pattern of the nano nickel, zirconium, aluminum is given. X-ray diffraction pattern of the from 25 degrees centigrade to up to 1000 degrees centigrade is given here. The XRD analysis shows that the peak position for both gamma nickel and Ni-base shift towards the lower theta value with increase of temperature, whereas the peak position reaches to their original position after during the cooling cycle of this from 1000 degrees centigrade to 250 degrees centigrade. Degrees centigrade. Now, for the lattice, I have estimated from Rydberg deformment analysis, where lattice parameter is observed to increase with temperature linearly for both the phases, gamma nickel and Ni-base phases. The linear coefficient of thermal expansion as estimated from the increase of lattice parameter is plotted here with temperature. So we can find that both the gamma nickel and Ni-base phases exhibit similar, nearly same linear thermal expansion, which shows their thermal stability, high thermal stability at high temperature, which is actually beneficial for alloy to be used at high temperature. And the linear thermal expansion is lower compared to the gamma nickel pure. The microstructure analysis ACM investigation shows that the no change of microstructure after annealing. This is the annealed sample of as solidified and annealed sample ACM images. No change of microstructure and no porcelain and no spheroidization occurs after annealing. Whereas the HRTM high resolution transmission vector microscopy image indicates the evolution of small precipitates after annealing for up to 120 hour annealing period and 160 annealing. After 160 annealing, whereas no change of no evolution of precipitates or observed in binary alloys. Here, some other images also shows that the small precipitates evolved after annealing for gamma nickel dendritic phases, whereas no such precipitates is evolved on Ni-base phases. In dark field images, the contrast becomes different, and in other images, we can find that the evolution of precipitates on gamma nickel dendritic phases. Here, high resolution microscopy image shows that the lattice interplanar spacing has been estimated from this precipitate phase and the matrix phase. Here we can from there we estimated the lattice parameter of the precipitate phase and the matrix phase. And in SAD pattern, we observed that the several L12 spots, 110 in this spots is evolved on the excessive SAD pattern, whereas in this SAD pattern we can observe the several L12 spots coming from a precipitate phase, which is precipitate phase. The engineering stress strain and stress strain plot of this diagram shows that the annealed sample exhibited into yield strength after annealing, and that this is two strain diagram shows that the improved of strength after annealing, whereas the two strain diagram plotted in log scale to estimate their strain hardening exponent, and strain hardening exponent at different plastic strain design is plotted here. And we can observe that the strain hardening exponent decreases with annealing time, and strain hardening rate is improved after annealing after annealing due to the interaction of the precipitates with the dislocation and the formation of pore loop. And here the dislocation strength of the yield strength, ultimate compressive strength, plastic strength, and hardness of the alloys is given here. We can clearly find that the improve of yield strength and ultimate compressive strength and also plasticity after annealing is observed. And here the projected yield strength is here the yield strength is projected depending on the various empirical equations. In the precipitation hardened alloy, as the precipitation alloy, the lattice parameter of the precipitate phase is different from the matrix phase. So coherence strengthening is occurred, and shear modulus of the precipitate is different from the matrix phase. Modular strengthening and order strengthening, because the precipitate is ordered, so order strengthening is observed. And so the contribution from each strengthening mechanism is estimated, and for the precipitate shearing mechanism, and in precipitate bypass mechanism, this is O1 mechanism. The contribution from O1 is also estimated, and we can find that these two curves, this is for shearing and this is for bypass mechanism. So these two curves cut in this point, which is the critical radius. In this point, the shearing is at lower critical radius. Shearing mechanism is dominant, and at higher critical radius is bypass mechanism is the dominating mechanism of strengthening. And improved summary of this chapter and improved of yield strength and hardness in annual x equals to 4 NEC is attributed for the evolution of 0.9 volume percentage of the for AN60 and 1.02 volume percent for AN128 samples of 2 to 15 millimeter size ordered L1 to type precipitates on the disordered gamma-nickel matrix. The precipitation strengthening is occurred by both shearing and bypass mechanism, in which critical radius of transition between shearing and bypass mechanism is estimated to be 3.8. The strain hardening of the NEC is observed to occur in three phases: stage 1 rapid and linear drop of theta strain hardening rate. Here we can linear strain hardening rate in 3 stages strain hardening observed, and theta and beta value strain hardening and dynamic recovery value of the annual sample is derived from the graphs of Fox making stream models is plotted and treated with the similar values estimated by using extended KME models. Equation for the precipitation hardened alloy, very large value of strain hardening rate value obtained for the annual specimens as compared to their A-size specimen is attributed due to the formation of pore loop storage for the presence of nano precipitates which of radius greater than RC, critical greater than RC. Whereas large increase of dynamic recovery 31 to 72 is caused by the fast dynamic recovery at stage 1. The microstructure of the nickel zirconium aluminum NEC is remain stable even after 1000 degrees centigrade without any polymorphic transformation. However, lattice parameter of both gamma nickel and NiBase increases with temperature. Nearly same value of the linear coefficient of linear thermal expansion for both the phases should reduce the internal stress generation for the dissimilar expansion of the mixture of phases in the alloy at high temperature. My final chapter is superior oxidation resistance of nano ultrafine nickel zirconium eutectic composites in the temperature range 500 to 900 degrees centigrade. In this slide, we can the mass gain plot is given here. In all the NECs exhibited mass gain in at 500 to 900 degrees centigrade. However, the mass gain increases with increase of temperature, and mass gain varies between 0.9 to 11.2 mg per centimeter square from 500 to 900 degrees centigrade. The major peaks at NIO and with trace amount of gamma nickel and ZrO2 after 700 degrees centigrade. In the specimen oxide phases in the oxide scale, is characterized here. In all the cases, the scales are mainly NIO and very trace amount of Jayanta and gamma nickel phase. Now this is the top surface and cross section of the oxide scale. In top surface, it is the we can find that the increase of NIO grain size with temperature. And the very as the gamma nickel and Ni5 data has different oxidation resistance, therefore the oxidation the gamma nickel dendritic phases surface can be distinguished even after oxidation at 600 degrees centigrade. And whereas with the uniform gradual increase of thickness of the oxide layer, the gamma nickel at higher temperature covers the oxide state fully covers the outer surface of the both gamma nickel dendritic and eutectic matrix. Increase of NIO gases with increase of temperature, size of NIO grains remains similar for both X0 and X4 NECs. Increase of thickness and internal oxidation at high temperature. Here, in the cross section of the oxide scale, we can find three distinct layers, that is unaffected base alloys, where internal oxidation region and the oxide scale, where oxide scale and internal oxidation region thickness of their thickness increases with increase of temperature. The elemental mapping shows that the oxide scale, this is the mainly zirconium oxide scale is mainly composed of zirconium and nickel and oxygen element, where the this is zirconium depleted region, where the zirconium is formed below the this region. So it can be said that the zirconium oxide is formed below the NIO layer. And the oxidation mechanism, there are two-way diffusion of oxidation mechanism, where cation and electrons moves towards the scale layer interface, whereas the anion and holes moves towards the base alloy scale interface. And internal oxidation region formed as the oxygen and hole moves towards the base alloys. And this is the NIO form at the outer region, where gamma nickel and Jayanta form at the just below the NIO scale. And the rate exponent shows that the oxidation NEC exhibited nearly parabolic at 500 degrees centigrade with rate exponent 0.45 to 0.56, whereas subparabolic with this rate exponent 0.21 to 0.37. And their parabolic rate constant is estimated with oxidation time. The mass change of the NECs is compared with the other nickel-based polycrystalline superalloys. Effect of nano ultrafine. Here we can see that our investigated NECs exhibited very superior oxidation resistance property, which is very much comparable with the other nickel-based polycrystalline superalloys. This is the region where at up to 0.8 normalized oxidation temperature. This is for as an example, this is for superleaf 75, where exhibited around 80 mass loss after 20 hours of oxidation, whereas mnemonic 90, which exhibited after 120 hours of oxidation around 11 milligram per centimeter square, which is comparable with the our investigated superalloys. And this diagram shows that the contribution of the lamellar high density of the lamellar surface for the oxidation behavior. Here with constituent phases, individual constituent phases, Ni5, Jayanta and gamma nickel, their oxidation mass gain is plotted here, and the mixture of the phases, which similar to the Ni5, our nickel, zirconium, aluminum composites, is lies here. The mixture in which the mixture of phases, gamma nickel volume percent in the NEC is present in form of either gamma nickel dendritic phase or in the gamma nickel lamellar eutectic phase. So total volume percentage of the gamma nickel lies around about 60%. Where but if the this line should follow the NEC, mixture of the phases should follow this line. But the oxidation of the NEC is actually somewhat higher than this because of the presence of ultrafine microstructure. This ultrafine microstructure causes faster diffusion path of the cations and increases the oxidation slightly. The summary of this chapter: all the NECs exhibit superior oxidation resistance at 500 to 900 degrees centigrade at very high normalized temperature at 0.8 pm is comparable with the existing nickel-based superalloys and other nickel-based polycrystalline superalloys. The oxidation kinetics of the NECs are nearly parabolic and at 500 degrees centigrade and subparabolic at 600 to 900 degrees centigrade, indicating the formation of protective oxide layer with time. Small increase of parabolic rate constant at higher temperature resulted slight increase of mass scale with increase of oxidation temperature. NIO and gamma nickel have formed at the outer and sub-layer of the oxide scale respectively, whereas very small amount of zirconium oxide has formed below the NIO, which is adherent with the base alloy and protect the alloy from further oxidation. The gamma nickel phase as appeared in the oxide scale is mainly due to the oxidation reaction of Ni5Zeta. And the cations nickel +2, zirconium +4, and Al +3 cations and electrons migrate towards the scale air interface, assisting the scale to go at the scale air interface. Measure delta W mass gain value of the NECs in between the delta W value of the individual constituent phases. A higher fraction of laminar interface provides easy outer diffusion path and assisting to grow the oxide scale exhibiting shorter transient state. The overall conclusion of my thesis is all the rods and ingot shows the presence of alternate nano-lamellar soft gamma nickel and hard Ni5Zeta intermetallic and micrometallic dendritic gamma nickel phase. Aluminum preferentially dissolved in gamma nickel phase. Lattice parameter of gamma nickel phase increases upon aluminum addition. No change of lattice parameter for Ni5Zeta upon aluminum addition. Boron percentage of the gamma nickel increases with upon aluminum addition for all ingots and rods, which varies from 20 to 31% in case of instant and hardness. With the microstructure refinement for increased cooling rate, very low standard sensitivity varies from 0.08008 to 0.0102. Standard sensitivity increases with reducing lamellar thickness but decreases with solute content. Dislocation control deformation mechanism for the entire lamellar thickness region 39 to 75 nanometer. Increase of instant and hardness is obtained through precipitation hardened alloy with evolution of nano precipitates. Microstructure is stable even up to 1000 degrees centigrade without showing any hint of polymorphic transformation or spheroidization. Low mass scale at higher normalized temperature up to 0.8 pm. Nano ultrafine lamellar microstructure slightly increases the mass gain of the composite. The scope for future work is the study of room temperature tension test and bending test and study of nano indentation. Some list of publication from thesis work and other publication is given here. List of conference which I attended, national and international conference which I attended. The acknowledgement.
Okay, Anushree, thank you. Anushree, you are done, na? Okay, thank you very much. And you completed within 45 minutes also, less than that. Although delivery was little quicker also. Okay, anyway. As customary, I think Professor Bhattacharya, you should start with some queries or anything on this thesis.
Yeah, thank you, Dr. A. And I will request Anushree to go through the response to the reviewers' comments.
I request all the DSC member to switch on their camera, please. Yes.
Yes. Okay.
Professor Bhattacharya, you want to say something on screen?
Yeah, I have switched on my camera.
Yes. I
Yes,
just
yes.
took a picture actually. Okay, so Anushree, since you joined, I hope the DSC member and the head of the department, DSC chairman, would like to say you something.
Yes, sir. Oh, I would like to congratulate Anushree. Congratulations, Dr. Anushree Dutta. Thank you, ma'am. Dr. Anushree Dutta. Thank you, ma'am. Congratulations. I'm very, very much happy to do research.
Okay.
You have done a great job. Yes, sir.
So I just like to remind you everybody that Anushree did BE from Durgapur Engineering College. At that time it was National Institute of it was RE College, Regional Engineering College, Regional Engineering College. And after that she has done a master's degree from Jadavpur. After that 8 years she had worked in Dostur, and after 8 years of professional experience in Dostur, she realized that she need a PhD degree, and she joined us through a NRB project. So Anushree, because of the pandemic, maybe we lost little time, but nevertheless, at the end of around 5 years, you able to finalize this thing, and so we all, as a supervisor, I am very much happy. And you have done really some good job on the development of nickel-based alloys. Okay, I mean, I have initiated those nanotechnic thing from 2005, and all kind of these mechanism like rotation and all these things. Those are in 2005 I published in Applied Physics Letters and many other journals, along with many of my colleagues. But nevertheless, I am very happy that young people are continuing those work and getting still some exciting things in it.
Yes, there is honestly you have contributed significantly, especially on that alloy, that is the nickel zirconium alloy. You have incorporated the zinc, and you have seen that is the aluminium, and then what is zirconium. That is absolutely your contribution, and that is that thing that is excellent work done, very little work done. And now you are doctorate, okay, Dr. Anushree Dutta, congratulations. And I think Professor Bhattacharya want to say something.
Yeah. No, I think many congratulations, because eutectic is something which is also a bit close to my heart as well.
Oh,
okay. So, of course, not India, because we have worked more towards this high-end of eutectic alloys. But anyway, the many concepts are similar. Many concepts and many fundamentals are similar. So I enjoyed reading the thesis, because it was, of course, quite close to the our heart. So I enjoyed reading the thesis, and many congratulations and best of luck for your future.
Thank you, sir. Thank you very much. Thank you all DSC members. Thank you all the professors.
And also it is a good opportunity to see many of my things. Like Devalaya, I could not speak, and he is usually very silent. And it was good to see Dr. Das and Dr. Indrani, and of course Dr. Roy. It is very, because now we are in a situation where only the possibility is through our virtual.
Right.
We are in a virtual world, and we do not know when it will really be our own world.
Very gloomy.
So from tomorrow onwards, we have a lockdown. So immediately after we finish, we have to gather our supplies for the lockdown. Prepare for the lockdown from tomorrow.
Yes.
Okay, so one thing, Professor Bhattacharya, it is a common custom from our group to give some sort of small memento. So actually, since there is no availability of sweets online, so I will send you the memento to your home address. I mean the residence address actually. Okay.
Okay. Thank you. I will send you. Thank you. Thanks for the nice gesture.
Thank you.
Okay.
Thank you, everybody. Thank you so much.
As well as Anushree's supervisor, who has done a great job supervising her. So congratulations to both.
Thank you, madam. Thank you, Professor Parvidas and Professor Jijira and everybody. Thank you, Professor
Thank
Bhattacharya.
Okay,
Yes.
bye then.
Yes.
Stay safe and take care.
Yes, thank you.
And
Thank you, sir. Professor Bhattacharya, but what about the other PhD members?
Yes, all the other DSC members.
Okay, I'm not officially the DSC member, so I'm not asking for myself.
No, it's fine. It's fine. Fine, madam.
Okay.
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 Thank you.
Okay, bye then. Thank you all.
Yes.
Okay.
Bye.
Bye. Thank you, sir. Thank you, sir.